All right, let's finish section 4.5. The real zeros of a polynomial function. And we had gone through our division algorithm, factor theorem was an important thing. And the last thing we covered in the video was the intermediate value theorem. So let's pick up after that with the idea of solving a cubic equation. Just as we have a quadratic formula that gives all the roots of a quadratic equation, using the book's terminology as consistently as I can, ax squared plus bx plus c equals 0, quadratic formula will give you both of the roots of that second degree polynomial. It'll give you the complex roots if there's complex roots. It'll give you the real roots if there's real roots. It'll give you rational, irrational. In the sense it's flawless. There are two roots, possibly real, possibly not. Doesn't matter. If they're complex, the quadratic formula will tell you those roots. This idea, as we saw when we derived the quadratic formula, involves completing the square, a very geometrically suggestive term. This was known to the Babylonians and maybe in a bit of a limited sense known to the Egyptians as well. So can't tell you who invented or discovered the quadratic formula. But we want to take this idea of thinking of this as a second degree polynomial equation and move to a third degree polynomial equation. Suppose we had the polynomial function ax cubed plus bx squared plus cx plus d set equal to 0. Is there a formula for this cubic equation, just as there is a formula, a quadratic formula, for this quadratic equation? The answer is yes, but discovery of that took quite some time. It was around the year 1535, Tartaglia comes up with a cubic formula that gives the roots, all of the roots of the third degree polynomial equation as given here. And this could well involve complex numbers also, though complex numbers were not really so much on the table as part of the number concept in 1535. In 1535, negative numbers were arguably recognized as numbers themselves. Numbers were thought of largely in terms of quantities and fractional parts at that point in history. But even the quadratic equation will give you the complex numbers solutions if you'll let it. Tartaglia's cubic equation will also, if you manipulate it properly, will give complex solutions to this system of equation as well. I'm sorry, to this third degree polynomial equation also. So third degree, there is a cubic formula. We will not look at it in its full glory. We'll look at some special cases of it. This was 1535. 5 years later, a chap named Ludovico Ferrari produces a quartic formula, a formula that will produce all four of the solutions to what's given by taking a fourth degree polynomial equation and then setting it equal to 0. Set this equal to 0 and solve for x. So there's a formula for first degree polynomial equations. We don't need a formula there. Those are easy enough to solve. There's the quadratic formula for second degree polynomial equations. There's a cubic equation for third degree polynomial equations. And there's a quartic equation for fourth degree polynomial, quartic formula for fourth degree polynomial equations. But then the mathematical world got stuck. So they produced these three formulas for zeros, formulas getting progressively more involved. One reason we won't state the general cubic equation is it's so messy. It's not a practical thing so much to use that to solve third degree polynomial equations. And similarly with the quartic formula. But what about a fifth degree polynomial equation? Or what about nth degree polynomials? Well, They couldn't work their way past fourth degree polynomials. For 300 years, there was work done looking for a quintic formula, you might call it, a formula that gives all of the zeros of an equation that results from setting a fifth degree polynomial equal to 0. Well, the reason they got stuck is there ain't such a formula. It was shown in the early 1800s that a quintic formula does not exist. This was shown first in the work of Niels Abel in 1821, was later generalized by Évariste-Galois in 1830. For details on this, got to refer you to sort of a senior level class. I have some notes, click on a link here. Why the hell am I in this class is what I subtitle this presentation that ties together some things you'll study in a modern algebra class with the things you'd study in a classical algebra class like Precalculus 1. So the material we're covering here is still addressed in senior level classes. It's things you were introduced to in high school, yet quite involved stuff if we want to go into it deeply. Really what we need to extract from this largely, in my opinion, is there exist formulas for third degree polynomial equations and fourth degree polynomial equations. There do not exist algebraic formulas for higher degree. And the third and fourth degree are so unwieldy, we won't even state them in this class. So in this supplement, we're going to look at the cubic formula. I'm going to run through a set of 8 problems related to the cubic formula. So to complete this section, we'll just look at cubic formula problem number 1 through number 8, and the remainder of the time we'll spend going through these algebraic manipulations. This is going to be largely uninspired and very mechanical. It's just following the algebraic proofs. We'll give a couple of examples at the end to illustrate the use of this narrow form of the cubic equation that we'll have. First question is, show that the general cubic equation y cubed plus by squared plus cy plus d equals 0 can be transformed into an equation of the form x cubed plus px plus q equals 0 by making a certain substitution. All right, first off, this isn't entirely a general cubic equation. The leading coefficient's been chosen to be 1. If it wasn't 1, you could always divide both sides by whatever this parameter is, a. If a is the leading coefficient and you have a y cubed plus by squared plus cy plus d equals 0, divide both sides by a. This then becomes 1. These others get modified, but still there's some particular real numbers. So this isn't as general as possible, but that's not a problem. We could translate any cubic polynomial equation into this form simply by dividing by the leading coefficient. And then the result would be in this form. So this is, in that sense, it's general. It's general enough. What we're going to do is make this substitution they tell us to make, and then just follow the arithmetic. They say let y equal x minus b over 3. B is the coefficient of y squared. So we're going to make that substitution. And this third degree polynomial in unknown y is going to become this third polynomial equation in unknown x, where x and y are related as given. Now the difference between these two equations is, never mind the fact one's in terms of y and the other's in terms of x, that's the unknown. Here, there's a term involving the unknown squared. Here, there's not a term involving the unknown squared. We've got the unknown cubed, no unknown squared, no x squared term. We get the unknown and the constant. So apparently by making this substitution, we can lose this term here and produce a somewhat simplified cubic equation. And we'll show how to solve this. If you can solve this, then with the appropriate substitutions, you can solve this, and you can even deal with a case where the leading coefficient is not 1. So we are this close to talking about the general solution to a cubic equation, the general cubic formula. All right, well, they tell us what to do, so we'll just do it and watch the algebra happen. Set y equal to b minus 3, because that's what they told us to do. In so doing, y squared, that would be x minus b over 3 squared. FOIL it, that will produce first squared, twice the product, last squared, that produces this. To cube it, we'll take x minus b over 3 and multiply it by x minus b over 3 squared, which we see from the previous line is given by this. Also, we had a formula to cube binomials in our past, but let's do it one step at a time. If we take the x and distributed it over these three terms, that gives us an x cubed minus 2bx squared, distributing over 3, plus b squared x over 9, say. Distribute the minus b over 3, that will give a minus bx squared over 3, minus bx squared over 3, there it is. This times this will be positive 2b squared x over 9, 2b squared x over 9, multiplying numerators and denominators. And finally, negative b over 3 times b squared over 9 will give us negative b cubed over 27. Collecting things together, simplifying a little bit. Let's see, here's the x cubed. About x squared terms. Here's an x squared term. Here's another x squared term. So we've got minus 2b x squared over 3 minus another b x squared over 3. That would leave us with minus 3 b x squared over 3. We'll further simplify in the next step. That takes care of the b squares. The x squares, but the x's. Here's a b squared x over 9. Here's a 2b squared x over 9. Common denominator, add them together, giving us 3b squared x over 9. And this is the only constant term, so that carries over. Simplifying a little bit more, we can cancel these 3's, giving us a minus b squared. We can cancel this 3 with that 9, giving us a b squared x divided by 3. That's given here. So cubing y produces this. Again, we had a formula for this in our past. We could have done that maybe a little bit more quickly, but this shows all the details. All right, so we now have y squared, and y cubed, each in terms of x. So what we're going to do is plug into this formula, like they told us to do, this value of y. Then in the formula, 0 equals y cubed plus by squared plus cy plus d becomes 0 equals y cubed is this quantity. We found it right here. Plus b, y squared. Y squared is this quantity. We found it right here. Plus cy. We started all this with y equals x minus b over 3. And there's the plus d. So all we did was substitute in for y cubed, this quantity, y squared, this quantity, y itself, this quantity. That produces this. Let's simplify. Let's run through, I guess, all the details on this. I will bore this arithmetic pretty quickly. There's only one x cubed term. How about x squared? Those are supposed to disappear. Here's a minus bx squared. Here's a plus bx squared. So those two will cancel. And indeed, that's the only x squared terms. So the x squared part has disappeared, as it's supposed to. X terms, here's a b squared over 3, positive b squared over 3. Here's a, let's see, distributing, it'll be negative 2b squared x over 3. Another x term, here's a cx. So we'll be left with the, let's see, b squared x over 3 minus 2b squared x over 3. Let's see, combine these two, that'll give us b squared x over 3 minus 2b squared x over 3, 1b squared x, or negative 1 b squared x over 3. Oops, there it is, negative b squared x over 3. Negative b squared over 3, here's the x on the side. So the books do balanced. All right, combine these two and that produces this term. Cx, here's a cx term right here. Now for the constant terms, we've got this, negative b cubed over 27, b squared, oops, b cubed over 9 when we distribute, giving us a b cubed over 9, and a c times negative b over 3, and then a d term. So constant term, constant term, constant term, constant term. Let's see if we can make the books balance there. The d, there it is. Distribute, that'll give us negative bc over 3. There it is. So we need to combine these two terms. This, when you distribute the b, is also a b cubed term. So we got negative b cubed over 27 plus b cubed over 9. Let's take b cubed over 9 and write it 3b cubed over 27. Multiply numerator denominator by 3. Good idea to pause and double check this. But distributing, this will give us 3b cubed over 27. Subtract b cubed over 27 will leave us with 2b cubed over 27. So the books really do balance. What we got here in the last line is an x cubed term, an x term, and a constant term. And that's what we were after. It must be that p equals this quantity here and q equals this quantity here. They simply told us to transform it into that form. They didn't tell us what p and q was. Well, we figured out what p and q was. So continuing, here's where we left off. We had 0 equals this. All that factoring stuff left us with this thing here. And so this is of the form x cubed plus px plus q equals 0, where this thing is p and this thing is q. So there's a transformation. What we have accomplished is taking a fairly general cubic equation and transferring it into a different kind of cubic equation that doesn't involve the unknown square. So you give me any cubic equation, even if the coefficient isn't 1, I can manipulate it and turn it into one of this form. I'll use a different variable, but that's okay. If I can solve this form, then we can solve the general form. And that's what we're aiming to do in the next problem or two. In the equation, x cubed plus px plus q equals 0. So that is, I think the book at some point calls it the depressed cubic. We've lost the x squared term, is effectively what it is. But any cubic equation can be put in this form. They say replace x with capital H plus capital K. Let 3 times h times k equal negative p. Show that h cubed plus k cubed equals negative q. Okay, I don't see a motivation for that at this stage, but it's just algebra. So we'll make the substitutions and this should happen. With x equals h plus k, we're going to need x cubed. So we'll take h plus k cubed. That's h plus k times h plus k squared, which is this quantity here. If you will distribute as we did previously and collect together common terms, it will produce this. If you recall how to cube a binomial, this little pattern with the exponents and this little pattern with the coefficients may look familiar to you. But all the details are given there. Let's not read through it. We just did something like that with different letters. Next, they want us to take 3hq equal to negative p. Okay, or maybe better yet, p taken to be negative 3hq. In that case, we can take this original formula in terms of x's, p's, and q's and express it simply in terms of h's and k's And I guess we'll still be stuck with a q. We're supposed to get this relationship between the q and the h's in the case. But making the substitutions as suggested, 0 equals x cubed plus px plus q. X cubed, we saw, is this stuff here. So we'll put that in, surrounded by parentheses. There's the x cubed. P was negative 3hk, so here's the p. X itself was h plus k, making that substitution, and we still got the q in there. Let's multiply out and see what happens. All right, so we'll simply copy this back down. Here it is with the parentheses gone, distribute here. Negative 3hk times h, negative 3h squared k. Negative 3hk times k, negative 3h k squared. And then the q comes along for the ride from here. Some things cancel. Here's a positive 3h squared k. Here's a negative 3h squared k. That and that cancel. Here's a 3hk squared. Here's a negative 3hk squared. That and that cancel. So we're simply left with h cubed plus k cubed plus q, as stated here. That, remember, we got into this having it set equal to 0. That equals 0. Take q to the other side of the equation where it becomes negative, and we see h cubed plus k cubed equals q. And don't know why, but that's what we were supposed to show. We're walking our way through solving that depressed cubic equation. We're trying to solve this. Is where we're going with all these manipulations. So it takes a while. If it was easy, it wouldn't have taken until the year 1500 to discover. Based on cubic formula problem number 2, we have two equations. We had 3hk equals negative p. We had h cubed plus k cubed equals negative q. They say solve for k in 3hk equals negative p and substitute it into this equation. Then show that h is of this form. Give you a hint. Look for an equation that's quadratic in form. See the plus or minus the square root of stuff. Something's happening here with a quadratic equation. So in some sense, we're using the quadratic equation to find a cubic equation. Not surprising. Sounds like we might be doing something inductive. We're not. It's going to fail after we would have a 4th degree polynomial equation. So 3hk equals negative p, right? Then they told us to solve for k. Okay, we'll just divide both sides by 3h, and that'll leave us k equals negative p divided by 3h. We had h cubed plus k cubed equals negative q from the previous problem. So we'll substitute for k, this quantity, giving us then negative q equals h cubed plus k cubed. Negative q equals h cubed plus k cubed, where k takes on this value. Not riveting stuff, but the algebra is going to work out. Do the cubing. This will become negative p cubed. Denominator will become 3 cubed times h cubed. It's 27h cubed. Produces this. Let's multiply both sides by h cubed. That'll get rid of the h cubed in the denominator, at least. We're ultimately trying to solve for h, right? We're showing that h equals this quantity here. So let's get those h's out of the denominator. Multiply both sides by h cubed. In this equation, negative q equals this. Multiply both sides by h cubed. We'll pick an h cubed up over here, giving us negative qh cubed. We'll have h cubed times h cubed, which is h to the 6th. We'll have h cubed times this stuff, and that cancels. And that's the reason we did this. We've gotten the h out of the denominator. So what we have here, if we rearrange this, is a kind of quadratic. So let's take the h to the 6th first. There we go. Bring this to the other side. It'll become a plus qh cubed, plus qh cubed. And then we have the minus p cubed over 27. We brought everything to one side of the equation. The other side will be 0. That we can solve. But it takes a trick. Notice h to the 6th is h cubed squared. We got an h cubed here as well, so we can treat this as h cubed squared plus q h cubed minus p cubed over 27. That's a quadratic where the unknown is h cubed. All right, cover up what's in the parentheses here. We've got unknown squared plus q times unknown, the constant, set equal to 0. It's a quadratic in the unknown h cubed. Treat it as a quadratic that we throw the quadratic formula at. A is 1, B is q, and C is this thing. So we will solve for the unknown, which is h cubed. We'll have to take a cube root, but look at that, h has a cube root in it. We'll substitute in for A, B, and C. A was 1, leading coefficient is 1, so we get a 1 there and there, here and here. B is the coefficient of the unknown, which is q, so we'll get a q here and here, there and there. And C was this negative p cubed over 27. That'll get tacked on the end, and that goes there. So we have solved this for h cubed. The hint was look for a quadratic. There it is. It's a quadratic in h cubed. But we can solve for h cubed. Going to the next page, we'll just clean this up a little bit. Oops. So we'll eliminate the parentheses. We'll get a q squared. It's the 2 in the denominator. This will become plus 4p cubed over 27. Getting rid of the parentheses and the 1s and combining the negative signs. And produce this. So simplifying a little bit from the previous slide, this gives us h cubed. We can break this up. Just as we would add together when we had a common denominator, we can split this up over common denominators. Let me keep up with the plus or minus stuff. That's going to play a surprising role somewhere down the line. Producing this, having split it up, let's take 2 and write it as the square root of 4. I want to put this under a single square root. I'm trying to make it look like what they requested. So now I've got square root of the numerator over square root of the denominator. I can write that simply as a square root of numerator over denominator in this form. This we can split up into something of the form q squared over 4, right? 4p cubed over 4 times 27. Ooh, the 4's cancel, and we get a p cubed over 27. Carrying along the square root stuff, we had h cubed equals this stuff in terms of p and q. So h itself is the cube root of this stuff. And that's exactly what we were supposed to show. So we found h. Somewhere in here, we want to find x. But we've got x in terms of h and k, I think it was. Let's look at the statement of this one more time. We were to show h is the cube root of negative q over 2 plus or minus this stuff. And that's exactly what we've got. Cube root of negative q over 2 plus or minus. This is the stuff. Next, use the solution for h from the previous problem and the equation h cubed plus k cubed equals negative q to show that k equals this quantity. All right, here's where we're going. We're solving for x. We have x equals h plus k. You found out what h was in the previous problem. Now we're figuring out what k is in terms of p and q. P and q were the coefficients in the cubic equation related to variable x. In fact, this looks just like k, except this has minus or plus. I'm going to keep that ordering on the minus and the plus. The minus and the plus, in some sense, will correspond to the plus or minus that we had for the value of h. Okay, well, here's h from the previous result. We know h cubed plus k cubed equals negative q. It's given here. If we cube this, we simply lose the cube root radical and get the stuff inside, negative q over 2 plus or minus this stuff here. So here is h cubed. K cubed is added on to that. We're trying to find K. Well, let's solve for K cubed. Notice this only involves P's and Q's, and the other side of the equation only involves P's and Q's. So take this to the other side of the equation. That will give us negative Q minus this is given equals K cubed. Let's distribute that negative sign. Distributing the negative sign produces positive Q over 2. We're going to take that and combine it with this negative Q. Negative Q plus Q over 2 is negative Q over 2. I actually did the addition here. That's where this negative Q over 2 come from. It's not this. It's this plus this minus the negative. That produces this quantity here. Distribute the negative sign on the plus or minus, and we get respectively minus or plus. The square root of blah, blah, blah. K cubed equals this. Well, then K itself is the cube root of that, and that's what we were supposed to show. So we have now found, in terms of P and Q, H and K. Problem number 5 says use the results above the H and K values to show that the solution of x cubed plus px plus q equals 0 is this. So this is a special case of the general cubic formula. This doesn't apply to cubics that have x squared terms. That's okay. We could take a cubic that has an x squared term and turn it into one like this and find the values of P and Q and then do this. So we're not stating the general cubic formula, but we're this close to it. We've got access to it with all the stuff we've been through. So the claim is X will take on these values. And that's totally unsurprising because if you'll recall, this looks a lot like H and this looks a lot like K. We had X equals H plus K, where H, see, H and K had those plus or minuses thing in them. We had the cube root of this plus or minus that. For H, correspondingly for K, we had the cube root of this minus or plus that. Now the this and the that, they're the same in both H and K. The difference is when H is positive, K is negative. And when H is negative, K is positive. Well, how about this? One of them's positive and the other one's negative. I can't tell you which is which, but one of them involves the plus and the other one involves the minus. So we get the positive ones and we get the minus ones. So here's what H plus K equals. I can't tell you which one's H and which one's K, but I can tell you one of them is H and the other one's K, but I don't know which is which. And that's why it was important to keep up with a corresponding plus or minus, minus or plus stuff that we did earlier. And that's what we were trying to show, is that X equals this quantity here. And this allows us to then solve for X in this sense. We got into this by making these particular substitutions. If we check it, X cubed plus PX plus Q, we have X was H plus K, P was negative 3HQ, said at the bottom of the previous slide. Q was negative Q was H cubed plus K cubed, so Q itself is a negative of that. So we're simply checking to make sure this has worked. Cubit produces this in parentheses, H plus K cubed equals this. We've done that previously. Distribute produces this. The plus Q produces the negative H cubed minus K cubed. And we've done something similar to this before. This cancels with that, the 3H squared K plus and minus 3HK squared minus 3HK squared. Those two cancel. This time, the H cubed cancels with a negative H cubed, positive Q cubed cancels with a negative Q cubed, and ain't nothing but 0 left. It worked. So we can express X in this form, and indeed, this produces a 0 of a cubic of this form. So as far as we're concerned, There's the cubic formula. Some of the shortcomings of our version of the cubic formula doesn't allow us to have an x squared term. If we have an x squared term, we can take that cubic and turn it into a cubic formula of this sort, solve this, and then translate it back into a solution of a general cubic. The book chose not to go into that level of detail, and I guess I'm okay with that. Other problems are, there's 3 solutions to this, as we'll see in the next section. We found one of them. What do you know about the other 2? They could be real. This hasn't told you about them. They could be complex, and this hasn't told you about those either. Has it? I suppose potentially there's some complex numbers involved here. We're taking square roots of some quantities. If p were negative, we could certainly have something negative here and have a square root of a negative, and here comes a complex number, potentially. But we're shying away from that at this stage. So this is not the real general form of a cubic formula. Google it and you'll see why we haven't stated it. To write it out and get all 3 solutions would take at least a page of text, meaning it's unwieldy, it's impractical. But let's illustrate it while we got it. Okay, this reduced version, depressed version, as the book calls it, use it to solve x cubed minus 6x minus 9 equals 0. Well, this is of the form we were dealing with, where p is -6 and q is -9. Here's what we get for an x value. So plug -6 into p, plug -9 in for q, and what we get, skipping some level of algebra that I normally show. Let's see, -9 is be 9/2, right? 9 squared is 81. -9 squared is 81, I guess you should say. That's where the 81 comes from. -6 cubed. 6 cubed is 216. So we get a -216 here. We get a similar thing here, except the plus in front of the square root has become a minus in this case to produce this. If we simplify common denominators and simplify, trust me, this will simplify down to something of this form: 9/2 plus 7/2 cube root of, or 9/2 minus 7/2 cube root of. A bit of the detail is shown, but not all of it. 7/2 plus 9/2 is 16/2. That's 8. We get the cube root of 8. That's just 2. 9/2 minus 7/2 is 2/2. Cube root of 1. We get 2 plus 1 equals 3. So all of that to find that 3 is a root of this. See, 3 cubed is 27. Minus 6 times 3 would be 18, minus 9. 27 minus 18 minus 9, that's 0. So it worked. So there's an illustration of using the cubic formula. You got any other bright ideas of how you might solve this? We could look for rational zeros. That rational roots theorem was quite useful. And the rational roots theorem would include on the list the number 3. And so that would give us that solution in an alternate way. Another shortcoming of the cubic formula, yeah, it's only good for 3rd-degree polynomial equations of this form. The rational roots theorem may not work at all, but it's a good attempt with any polynomial. It's independent of the degree. I take it back. I did need integer coefficients, I guess, to use the rational roots theorem. So it's not good for any polynomial. So there's another restriction. Use the cubic formula to deal with this. Additional comments: use a calculator to give a decimal approximation of the solution to the equation. I don't like that. I'm going to impose it this time. You'll see why. We get numbers that, I won't say we can't handle them, but they're algebraically very horrible to simplify by hand. So in this case, we've got the coefficient of x, p is 3. The constant term q is -14. The cubic formula gives us this. So we will plug in p equals 3, q equals 14. We'll produce something like this, which further simplifies to cube root of 7 plus the square root of 50 plus cube root of 7 minus the square root of 50. This and this. So here's the value of x, and that's the thing we're going to plug in the calculator. So here's what we get for the x value. If you plug that into the calculator, lo and behold, you're going to get out x equals 2. That doesn't look like 2. If we were to manipulate it properly, we could show that equals 2. My first guess would be maybe we cube it and see what happens there. Cubing this might produce some useful stuff, but I'm going to depend on the calculator for this. We could analytically, algebraically, analyze this and show it equals 2. Quite tedious, I suspect, so I'm happy to take the calculator on this one. But here's the precise solution. Turns out that precise solution is actually 2, but it doesn't look like it. And there's another example of using the cubic formula. So as a final example, use the methods of this section to solve this. All right. We could use the cubic formula. P is 3, Q is negative 14. I think if we do, we get stuck kind of similar to something that happened in the previous example. We get a nice little number that we don't recognize because it comes to us inside cube roots with square roots inside of them. So it comes to this nested mess that might be a nice number. We just don't recognize it. I tell you what, we could do that. Let's just use the rational zeros theorem. So let's take the divisors of negative 14, plus or minus 1, plus or minus 2, plus or minus 7, and the rational divisors of the leading coefficient, a sub 3, which is 1, which is just plus or minus 1. We will take a ratio, P over Q, where P is a factor of negative 14, Q is a factor of 1, divisor of those numbers. So we'll have plus or minus 1, plus or minus 2, plus or minus 7, divided by plus or minus 1. That'll produce these 6 numbers. So nothing new comes out. I like those when they start with a leading coefficient of 1 or negative 1, I guess, in this case. The plus or minus 1 would be generated in either case. So we get this list of numbers. Let's just plug them into the function. I won't bore you with the details. You want to get this from a calculator. Not a bad idea, especially when you have to cube 7. The others are small numbers. But this will produce, what am I looking for? Looking for zeros, right? Not 0, not 0, 0, not 0, not 0, not 0. 2. X equals 2 is a 0 of this. They said solve the equation. Even if we used the cubic formula, it'd only give us one solution. Third degree polynomials, these always have at least one real solution, intermediate value theorem. Think about it. Big positive number, this is going to be positive. Big negative number, this is going to be negative, if it's big enough. Well, if it's negative in one place and positive in another, it's got to be 0 somewhere. Intermediate value theorem. These represent continuous functions. Here's one place where it's 0. There could be others, though. So it said solve it. Well, we found one of the zeros, x equals 2. That means by the factor theorem, x minus 2 is a factor of this thing. Let's do some long division. So let's take x cubed plus 3x minus 14 and divide it by x minus 2. The remainder will be 0. Factor theorem implies that. The remainder theorem more directly says this, but I know we'll get a remainder of 0. Do the long division. That will produce this is the quotient, this is the remainder. That means x cubed plus 3x minus 14 factors as x minus 2 times that quotient. That is a quadratic. Can you solve that? You've got the quadratic equation. I can find all of the roots of a quadratic equation. If we try to apply the quadratic formula to what we get, the quadratic equation that results by setting this equal to 0, the discriminant is b squared minus 4ac. B is 2, a is 1, c is 7. We find the discriminant is negative 24. Ooh, that's negative. So there won't be any real zeros of this. We know by the quadratic equation, and so we've thoroughly analyzed this one. 2 is a root, and it's the only root of this third degree polynomial. Excuse me, it's the only real root of this third degree polynomial. So on that sad note, we'll bring section 4.5 to an end. What I'm depressed about is, geez, if we could use complex roots, this third degree polynomial, that would have 3 roots. It'd have 2, and the 2 roots we would get from the quadratic formula. They'd be complex roots, but the books would balance, and we'd have a third degree polynomial with 3 roots, 1 real one and 2 complex ones. So to get me out of my state of depression, let's look at section 4.6. In 4.6, we'll consider what happens when you're allowed to deal with complex numbers. And lots of neat things, lots of neat algebraic things happen if you'll shift over and allow for the complex numbers. The next section is probably not part of the core material of Precalculus 1, but it's good stuff. The fundamental theorem of algebra is stated in the next section. So we'll go to fundamental theorem of algebra, section 4.6, and have a little video on that one as well. I'll see you there. Have a nice day. Bye.